Okay, cool. So yeah, we were talking about declination and right ascension. So who would like to tell me what declination is, first of all, and how is it universal? Why is it called one of the why is it a part of the universal coordinate system? Anyone? How about Manasa? Do you have any idea about the RA and DEC system, Manasa?
Uh, it's same like latitude and longitude, but just projected to the celestial plane, and its reference is the celestial equator. So declination is just like vertical angle, the same as uh, yeah, I think so. And right ascension is horizontal angle, I believe.
Okay, yes, that's actually a pretty accurate answer because you mentioned how it's very similar to longitude and latitude, right? So let's first talk about latitude. Okay, on Earth you have latitude in the sense some angular, value called say theta, and that is defined for any point and the center point of the Earth as well, right? So it's defined with respect to the equator. Um, let's try this. Hopefully it doesn't die this time. Yeah, so that is how latitude is usually measured. So what is declination? Declination is measured from the celestial equator. So you will say, oh, there is an angular rise from the celestial equator, and for this particular object, that is where it is. So this you can see that this is like a great circle. You can think of it as the celestial sphere, and you will say there is somebody at this particular point. For that particular person, what is the latitude? If this was the Earth, you would say, oh, there is some angle created here, and you would say that is the latitude. The same thing we are going to project into the celestial sphere. Instead of the Earth's equator, we are going to have the celestial equator. Same thing, but projected onto a huge, bigger circle, okay, which represents the sky. So the same definition applies for the declination. Okay. So let's say Jupiter is at a particular declination, or actually, it's better to think about a star at this point. So let's say there is some star over here and it's at a declination of 30 degrees. Let's say all of us are having like a sleepover on somebody's terrace, okay? And we are sleeping outside and staring up at the sky for the entire night. Okay. My question to you is, will the declination of that star change as time passes, throughout the night? Can anyone tell me?
Yes, because the Earth is also rotating, the celestial sphere is also rotating, and the star is also moving.
Okay. Who else can tell me if the declination of a particular star? Any other opinion other than what she said? So the star is over.
If you are at the North Pole, then the declination will not change.
Okay.
Right.
Mm-hmm. Mm-hmm. What if I'm not at the North Pole? Like you can see this angle, right? This is say 40 degrees, okay? Let's take, oh, we are at Bangalore. This is like 13 degrees maybe. But irrespective of what that is, you're looking at multiple stars in the sky and they are rotating this way, right? They're rotating across the sky, and the whole sky seems to rotate nicely, right? Why do we perceive that? Because the Earth is rotating. Like in reality, nothing else is rotating. Only the Earth is rotating. Okay, but because the Earth is rotating, everything else seems to rotate with respect to us. So this is apparent motion of the stars. So my question again is, in the apparent motion of the stars, is there a change in declination for a given star on a given night? I'll give you a couple of seconds to think about it.
Yes, there will be change in declination.
Okay, so the final answer from all of you is there will be a change in declination. This is a slightly, um, yeah, this is a image where I've defined D as the declination, okay? And you can see that RA is defined as the horizontal angle. But before we go to the RA, right, I want to emphasize a point about declination that all of you, I don't think you fully perhaps understood. So what is important is you are on the you're on any planet, right? And you have some axis of rotation. Yes, you have some axis of rotation. That is your axis of rotation, and that's your North Pole. But the stars are here. They are distinct, distant points in the sky, and they're everywhere. You are rotating. By the way, I asked this question last time. Does the Earth rotate clockwise or anti-clockwise? I hope you all remember. What was the answer?
Anti-clockwise.
Anti-clockwise. So for the anti-clockwise rotation, since we are anti-clockwise, the stars seem to move from here to here, right? So you see a star there, you're gradually approaching it, right? So it goes here from here to directly above your head in the zenith, and then the same star will look like it is going there. And this is nothing but east to west motion of the stars. So the apparent motion is east to west. We've established that. My question was, all these motions, they are defined across these big circles in the sky, right? And all of these circles are on this celestial sphere because this is the Earth, okay? In this case, I've drawn the Earth in the center. And there are these huge circles defined by these stars. And what you guys have kind of missed out on is that for a given star, the position of it is actually fixed on a greater circle. So in reality, the declination of a star does not change at all over the period of the night. So the position of the star is changing. But the answer you guys gave is wrong because the declination actually defines something called minor circles. Okay, so you've got large circles and you've got minor circles. Okay, so let's say now this is the celestial sphere. So if I draw a circle here, I'm actually talking about a minor circle. This is the equatorial circle, which is a great circle, right? Great circles pass through the center. So this is actually a smaller circle. It's badly drawn, but you get the point. So if I draw the same thing here, so what you guys have to understand is that the declination defines minor circles. Okay, so these are minor circles. And what is the declination? It's some angle to a point on the minor circle, right? And you're defining this point at this angle, and you're calling it declination. Great. But what is happening over the period of a night? What is actually happening is that the Earth is rotating, but in our system, we are not going to think about that. We're going to assume that the entire celestial sphere is rotating this way. But as it rotates, the star's position does not change with respect to the minor circle. It's constant. It's always on this minor circle. It's not going to leave that circle, which essentially means the declination of it will never change over the period of that night. Understood? So I hope that makes some sense. Please go back and think about it. But if you look at these images, right, they're called, I think, star astrophotography. Star Trek. Yeah, we don't need a Star Trek. Astrophotography. Did someone write something? It's not audible to her. Oh, okay. Is it audible to everyone else?
Yes.
Yes.
Okay. So if you look at these long exposure astrophotography, right, usually it looks like this. And you must be wondering, oh, like how is it defining these really big circles? And they really do look like giant circles. Why is that? Because actually each of these lines here is a great circle. It's a circle defined by a single star. So these are long exposure images, which are basically taken over the period of several hours or throughout the night, right? So as the night passes, you're going to see the trajectory of these stars, apparent movement of these stars. So they look like circles to you. Why? Because a star continues to remain on a circle. Its declination never changes. Yes, its altitude changes, right? Yes, its azimuth changes for a given observer. But declination is a universally defined parameter, and declination does not change. Okay, so that's what you have to remember. So I think through this diagram is what you have to remember every time you think of declination, because this is the celestial equator. Okay, and for the celestial equator, the star is exactly where it is throughout the night. Now, if the axis of rotation shifts, or there is a different part of the a different season, a different time during the year, the Earth keeps on revolving around the sun, then you're not going to see the same star and the same declination, right? But over a given night, it basically traces a huge circle. Okay, now let's go to RA, I think.
So it means like in 2020 the I have a star A. So the area declination is fixed in 2020. But when we see or want to take observation of that particular star A, so in 2021 or next year the area and declination of that star will be changed.
Yeah, no, actually, within 2020, it will change. That's why I kept repeating particular night, right? So over the
Okay.
period of that night, declination will be the same. Why? Because we are not factoring in a revolution of the Earth. We are only looking at rotation of the Earth. But when you look at
Okay.
6 months period of time, where is the Earth? It's on the other side of the solar system. It's on the other
Hmm.
side of the sun, right? So if it's on the other side of the sun, then the relative position of the star has definitely changed. Okay, so
Okay.
because of that, it's definitely going to be different. For example, here is the sun, and Earth is initially here, then it goes over here. Okay, let's say there is a very distant star somewhere over here. So initially, the declination is going to look like, oh, this is a celestial sphere.
So you know.
Yeah, declination will look like it's at 30 degrees north this way. And then if you go all the way over here, it might be an entirely different apparent angle that you see, right? So it will change over the course of a year, but it will not change for a given night. And it definitely depends on the orbital tilt. So there is something called orbital precession. I don't know if you guys have heard of it. We can touch upon this topic later. Orbital, how many of you have heard of it? Can someone tell me?
Yes, I know about the precession.
Okay.
There is a two term precession and second is the zigzag path. I didn't remember the term, but
Hmm. Okay. So precession of the orbit basically means that there is a particular orbit of rotation, right? Orbit. Yeah, there's a particular orbit to the Earth, but what is happening is that tilt, that object, sorry, that angle itself is moving. Okay. So if you think about, um, let's open this link. So you can look at this particular, axis of the um, Earth right now, and today it looks like this. But as it's moving around the sun, what is happening is this entire orbit is actually precessing. So the tilt is actually not constant. So most of us learn only about two kinds of motion of the Earth, right? Like in high school, we learn about, oh, there is rotation, there is revolution. But there is actually something called orbital precession that is also taking place. Why do you think they don't mention it in most books? Or why do you think we don't account for it in maybe yearly astronomical calculations? Any idea why this looks like an important aspect to counter, right? You want to take account of it if you're doing astronomy, and the entire axis of rotation supposedly is constantly moving, and it changes its angle of tilt. So why are we not taking account of this in like smaller calculations? Any ideas?
I think, as you said, it is constantly moving. So I think that is the reason. If it was variable, then it would like change everything.
Mm-hmm.
But
So, okay. Yeah, so the actual answer is this is an important motion. In fact, this changes the apparent positions of the stars entirely. Okay. So, you know, if you're pointing here, the north celestial pole is somewhere here. Imagine the entire orbit tilts, your north celestial pole itself will change. It's a very drastic change. The reason we're not accounting for it is actually because it's very slow. Okay. The precession is happening over something like 26,000 years, if I'm not wrong. Precession, the change in orientation of the Earth's rotational axis, alters the orientation of the Earth with respect to perihelion aphelion. Okay, so this timeline is on the order of around 26,000 years. Oh, there's a bit of noise.
I think the in astrology the horoscope and the motion of sun is also depend on this precession, because in 14th of Jan we like Makar Rashi and all. So I
Yeah,
think
yeah.
that was also.
Actually, it's a good fact. So Indian astrology, right? If you go to Indian astrology, I'm not talking about Western astrology for a reason. It's a bit different. Why are these two different? Because the Indian system takes into account precision. Like that's how accurate their calculations were. So in the astronomical texts, there are a lot of texts like Surya Siddhanta and things like that that people wrote. Like astronomy was a very active field. And even though they used astronomy in the context of astrology in most cases, in several cases, they always accounted for the precision. So even though it was astrology, it was accurate astrology. But Western idea of horoscope, right? It doesn't really account for any of this. So yeah, this is an important thing to keep in mind. So the precision is also happening, right? So anyway, you guys learned about declination right now, and you know that the declination is constant on a given night. These stars are tracing out big circles, and these big circles are defining something called minor circles on our celestial sphere, which you saw over here. This is your celestial sphere, and these are your minor circles. Okay. Now again for RA, what am I going to do? I'm going to draw something that resembles longitudes. Right? Simple. So I'm going to resemble it's going to resemble longitudes, and we have to draw it like this. So RA, as you can see, it kind of slices the celestial sphere into like these cake slices, right? It's like as if you're cutting a cake. So you should always, whenever I say RA, you should come to the picture of cutting a cake. It's longitudinal. And again, we need a reference for on Earth. We talk about, oh, the Great Meridian passes through the Greenwich in London or whatever, right? So we need a similar reference point. And I think Shalini was mentioning the first point of Aries. So it's basically called the vernal equinox as well. And we'll come to the ecliptic later. Ecliptic is the relative trajectory of the sun, okay, as perceived by us. Essentially, this is a point of intersection between the celestial equator and the something called an ecliptic, which you'll learn later. So that is called the vernal equinox, and from vernal equinox we calculate right ascension. So if it's this side, we say, oh, it's these many degrees, or people actually use something called hour angle more commonly. Okay. So they say these many hours or these many minutes away from the vernal equinox, and that is the reference you use to define right ascension. Okay. Now, polar angle is defined as 90 minus declination. So what does that sentence mean? You have some declination here. Declination is the red color guy. So the red color guy is declination. Let's say you want to say what is whatever declination, but with respect to the pole. So you'll draw one angle like that, and you'll say, what is this angle? So some systems use 90 minus theta instead of theta itself. Theta is declination. So that is called polar angle. They use 90 minus theta. Okay. Now every other declination can be represented as a minor circle whose plane is parallel to the equatorial plane. That is what I've drawn over here, right? They don't intersect. These are parallel planes to the equatorial plane. Note that the relative altitude of the NCP is always equal. Okay, this is a spoiler alert. So how many of you are on the Telegram main discussions group? I'd put out an astronomy task for anyone who might be interested. Okay, so that task is the official assignment for the coming few days. It will be put up on Classroom. I'll give you a quick tour of Classroom when this is over. But I don't know if you guys saw that. I can even fetch it for you from the discussions page. So this is something Aditya was working on. I'd just given it to him as the homework. So here is the question. So the question was quite simple. It basically said, what is the relationship between, I've sent it on the chat box. What is the relationship between the altitude of the north celestial pole at any given point and the latitude of that point? Okay, try to understand what that means. I'm just saying there is some horizon for every guy, right? Like wherever you are, there is a horizon for this person over here. In his horizon, he's going to see the North Celestial Pole. It's very far away. He's going to see that at a particular altitude, which is an alt-azimuth system parameter, right? We learned about it. He's going to see it at some altitude. How is that altitude connected to the latitude of where he is, the geographical latitude? That was the question. Okay. So I'm going to post the same thing on Classroom. You can all submit it over there. You can either draw a little sketch or whatever. And you have to tell me what the relationship is, why is it related like that, and so on. Okay, before that, does anyone have any clue or idea on how to solve that question? You can get creative with the submission. You can maybe, use a circular image you find on Google and draw over it or whatever you want, but you should be able to describe the solution well, okay? And it's actually quite simple. It's about perspective. That's the solution. It's about perspective. It's how you're seeing it. And then it'll become very obvious to you. I'll reveal the answer. I know it's been a while, but it's okay. You guys can think about it for a while. So on any given night, an observer will see the stars constantly along fixed circles in the sky and will observe the entire sphere rotate at 15 degrees per hour. As mentioned above, the declination traces out minor circles on the celestial sphere. Now, if we consider the radius of the entire sphere to be 1, for simplicity this is, which is also the radius of the great circle, then the radius of a given minor circle is given by, okay, so this is what we're talking about. So essentially what I'm saying there is, you've got some circle, and you've got a great circle which has a particular radius. We'll call it 1. Why? You'll come to know. It's for simplicity. So now I'll draw a minor circle like that. Okay. Now this center and whatever, this center is aligned, right? It's just the same center. And I'll draw sort of, yeah. Now, or maybe better, yeah, this is better to draw it like this. So this angle is nothing but the latitude of this place, right? Now, this is the latitude. Therefore, what is the radius of the minor circle? Can someone tell me? This is theta, okay? Theta is the latitude of that place. That place is on this minor circle. This radius is, you can call it r, let's call it r. This is the radius of the whole sphere. What is the radius of the minor circle?
R cos theta.
Yeah, it's r cos theta. I hope everyone got that. It's quite simple. So it's r cos theta because you can also just draw it over here, maybe.
Resolve the component of
Yeah,
R.
cos theta, and this is the same. So the radius of the minor circle, which means now we know a generalized expression for any minor circle on the Earth or on the spherical celestial sphere. So it's r cos theta. Note that theta here is also the latitude of any point on that particular minor circle. Therefore, the velocity of the path. So here we come to the concept of apparent angular velocity. Okay. Here you might say, oh, you've mentioned 15 degrees per hour, right? You're saying the whole celestial sphere rotates at 15 degrees per hour. So why are you trying to describe apparent velocity? Because in reality, if you stare out into the night sky for the entire, say, period of the night, there are going to be some stars that look like they have a higher velocity, and some stars closer to the pole which look like they are very slow. Why is that? Can someone explain it conceptually? Why would, yeah, the clue is the stars near the equator, the great celestial sphere's equator, look like they are moving extremely fast as you look out into the night sky. Okay, they're like, whoa, that's pretty fast. And then you look into some star that's closer to the pole, and you'll see it's fairly slow. So why is there a difference in the relative velocity of these stars? Can someone explain?
Hello,
Hello.
can you hear me?
Yeah, I can hear you.
Yeah, okay. I don't know the name of that concept, but it's the same reason why aerospace companies launch rockets from the equator, near the equator, because of that same some speed thing.
Really? Okay. Okay, Aditya, that's your homework for today. Okay,
Oh
or
my
tomorrow.
god.
So you have to tell me how those two things are related. So first of all, why do they launch rockets from the Earth, from the equator, instead of some other place? It's what you claim, at least closer locations closer to the equator. And yeah, why is that beneficial? Okay, those are some of the answers you're going to tell, and you can post it on the group. Okay.
Okay.
Yeah. But others, somebody else was trying to explain the concept. Like the whole question was,
Hello.
why is it? Yeah, tell me.
Because if a star is little far and one is near, both the stars should sweep the exact angle, that is 15 degree. So the one nearer has to travel lesser arc distance, and the farther one should travel more arc distance to sweep the exact angle.
Hmm. So, what do you mean by farther? Can you make it slightly more clear as to why those near the equator are faster? What do you mean by farther? With respect to what? Is it are you talking in terms of distance from Earth or something else?
I'm not sure.
Okay. So,
Actually, maybe the star near to the pole have a smaller circle, and far from the pole have the radius of the circle is much greater than compared to the previous one. So the arc length is greater when it far from the pole. So distance is directly proportional to the speed. So maybe that's maybe a reason.
okay, so close enough. I think both of you are very close to the conceptual idea. Okay. So what's happening is you're saying, hey, Earth is a solid sphere. Okay, let's just think about Earth now. Let's not go to the celestial sphere. But even on Earth, like Aditya was saying, right? It's a solid sphere, which means all parts of the Earth have to travel with the same rotational, same velocity, right? Like they have to complete 360 degrees in 24 hours, irrespective of where the point is on Earth. Which means for a small minor circle here, and if the point is on this circle, and there is a point over here on the equator, both of them have to traverse 360 degrees within the same 24 hours. But this guy has much longer to complete, like much longer distance to travel within the same amount of time. The angular sweep is the same, right? Both of them are sweeping 360 degrees. But because this guy is a part of a circle that has a larger radius, he has to travel more distance. 2 pi r, 2 pi r, correct?
Yeah.
So distance by time, time is constant here because it's a solid body. You're fixing the time. You're saying it's 24 hours. Then essentially, distance is if the distance is larger, your velocity is going to be small. Velocity is going to be higher, right? Velocity is directly proportional. So which are the fastest points here? The ones on the equatorial plane, right? So velocity equals distance by time. Time is constant. If distance swept is larger, then velocity is going to be larger. Very simple, okay? Same thing, expanded, projected into the celestial sphere. Everything has to do the same job of completing 15 degrees in an hour. But this guy has to travel a much more distance, right? The sweep is much more for him, so he travels faster than a star that has to travel over here. Okay, so actually, as you go closer to the pole, it almost looks stationary. So in fact, the NCP, North Celestial Pole, that's the shortcut we'll be using for all further conversations. So the NCP is practically stationary for any observer. Okay. Why? Because that actually represents the axis of rotation itself. So that can't move. It's like drawing a line through the celestial sphere, saying that, oh, the whole celestial sphere is moving around the line. So you can't say the axis itself is rotating, right? The axis is stationary, everything else is moving around. So the north celestial pole, which lies on the axis, is more or less stationary. Okay. Yeah, so this is Polaris, by the way, those of you who remember from the last class. Interesting fact, Polaris is actually a system of 5 star. It's a penta star system, like how you've got binary star systems. So it's very interesting. So you might want to go read up a bit about Polaris and how, I don't know, like in terms of stellar dynamics, how it's stable, right? Like with 5 stars in the system. So that's an interesting thing. So we go on and we describe the theta velocity as a function of theta. Why as a function of theta? We are defining something called apparent velocity for objects on each minor circle. This is a smaller minor circle. This is a slightly bigger minor circle. Each of them is going to end up looking like it has a different velocity. But please note that I'm emphasizing apparent because, neither are the stars moving, nor is it the fact that this part of the earth is traversing faster. It's just a mathematical consequence, and you have an apparent speed which is higher for stars in the equatorial region. So you get this expression 2 pi. I'm taking r as 1, so you won't see r in the expression. So instead I'll write 2 pi cos theta by t. Okay, so this is my expression for apparent velocity. So if you think about it, let's just call it 2 pi r, right? So for any object here, what is the velocity given by? Velocity is nothing but distance by time. Distance is nothing but circumference. So you got 2 pi r. 2 pi r. So now 2 pi r is there. So actually, if you think about it, time is constant. So v1 by r1, I can't draw it here, guys. Sorry, it's damn this thing. But anyway, you can visualize it. So v1 by r1 equals v2 by r2. So this establishes a constant relationship between velocity and radius. Did you guys understand that? v1 by r1 equals v2 by r2. You might want to write that down. So what do I mean by that? I can pick any radius, okay? And if I know the radius and I know the radius of another circle, then I also know the ratio of their velocities, apparent velocities, okay? So that is a constant relationship. Notice that the above equation implies that points on the equator move the fastest relative to us, while the points near the poles are essentially stationary. There is a constant relationship between apparent angular velocity and radius corresponding to that particular latitude. Angular velocity of any point with respect to the celestial pole is this. So now this last sentence talks about angular velocity of any point with respect to the celestial pole is 15. So this is the constant whatever we spoke about. With respect to the north pole, right? He doesn't care. He's just sitting there, and there are long, there are basically longitudes defined around him. So for him, any object, it doesn't matter which object you take, in 1 hour, it will move 15 degrees. So for him, this apparent velocity concept doesn't come into play. That only comes into play when you're somewhere on the earth, somewhere else, and you're looking out into the night sky, right? But with respect to the pole, every object has to sweep out the same 15 degrees, right? The same 15 degrees. That's an important point. Okay, so we finished these. So these formulas are important. Just keep it in mind. So now we can solve a couple of problems related to positional astronomy. I'll just give you an overview of what chapters we need to cover now, since we're going to be starting the brilliant lectures. I think some of you, like Shalini has been to some of our brilliant lectures, which is a great way to problem solve. So the prerequisite for this is just mathematics. You should know some amount of math. but also you should have a paper and pen in hand along with a calculator. Okay. And it takes a bit of patience. You're going to sit down, you're going to crunch through numbers, but it's a very practical way of learning these concepts. Okay. So Brilliant is a whole bunch of courses, but these are not available freely to other people right now. So Nakshatra has a special subscription to these courses. All right. So what I can do is I'll put somebody, another intern in chat, so she can host another session in the week where you can just solve the Brilliant problems as well. So we'll also be doing this. So a few important aspects are gravity, HR diagram, atomic spectra is important. Then we'll be talking about, this is a very interesting thing, Greek estimates. Yeah, all of these are important. Okay.